So yes, as Paige mentioned, my name's Sam Foreman. I'm a computational scientist here in the Leadership Computing Facility at Argonne National Lab. People who might be interested, my background is in high energy physics. And specifically, I did work, my PhD was on lattice QCD and machine learning methods for lattice QCD simulations. Since then, I've kind of gone on to spend a lot of time on large language model development and parallel training techniques. So this is actually kind of what I do a lot day to day. And it's a very active area of research, and I'll talk a bit more about it today. So as I was kind of mentioned or alluded to, I'll be talking today about parallel training techniques as part of the AI for Science training series here at Argonne National Lab. So there are some links here on the slides, but I also sent in the Slack channel links to the GitHub page with the README, as well as the link to these slides, so people can follow along. They're online if people are interested at that link. So before kind of diving into things, I think it's useful to maybe get a bit of perspective and see how we got to where we are today. And there's this kind of interesting study from OpenAI that was put out a few years ago, but captures the sentiment. And they looked at essentially the historical usage of compute resources used to train AI systems, going all the way back to the invention of the perceptron way back in 1959 or so, at late 50s. And what they found is that it can be roughly classified into these two distinct eras. So this first era being from the invention of the perceptron roughly through 2012, and then the modern era being from 2012 to the current day. And what they found is that in the modern era, so beginning from 2012 to the current day, that the amount of compute used to train AI systems or AI models has been increasing exponentially and has been doubling roughly every 3.4 months, which has resulted in an approximate 300,000-fold increase since 2012. And so if you just to kind of give some sense of scale, comparing that against Moore's law over the same period would have doubled only 7 times. So it really is this kind of exponential growth that can be seen in particular in this modern era. So this next slide just kind of zooms in on the period from 2012 to today. And it's worth noting that this is a log scale. So this is really kind of, you can see this really truly exponential growth. And they found that just comparing the amount of resources used to train AlphaGo 0 versus AlexNet, which was back in 2012, was roughly 300,000 times more. And so this really just kind of goes to show the kind of explosion in compute resources used to train AI systems, particularly in recent years, and is definitely, so this study is maybe a few years old now, but this trend has only continued since, and I would imagine will continue into the near future, foreseeable future, really. And so this is kind of you really just kind of to give a sense of the demand for compute resources, specifically for training AI, and kind of the general trend that this is, that the resource requirements have followed. And so I guess with that in mind, it's probably pretty obvious to many of you now that the techniques you've seen so far in this training course will not get you to the levels of compute needed to train something like ChatGPT, for example. And this is due in large part because all of the procedures we've seen so far have focused on training using a single GPU. And this is kind of just a rough, schematic illustration showing how this proceeds. So this is how we've done all of the training up to this point. We have some data set that we break into some sequence of mini batches. Each of these mini batches are fed one at a time into the model, used to generate some output. From that output, we calculate a loss and update the weights. But all of this is kind of limited in that the data progression proceeds one mini batch at a time. And so obviously this is not ideal and is really kind of this is not a very common scenario you'll see in training models at scale. And so this is typically much slower than what we'll see today, which is like data parallel and model parallel training. Another limitation of this type of approach is that the model capacity is ultimately limited by the amount of RAM in your GPU. And so you're only able to fit as large of a model as you can fit in your GPU RAM. And that's often, that can be in many circumstances pretty limiting. And so for training really large language models like ChatGPT and these types of very large, many billion parameter types of models, there's another kind of parallelism technique, which we won't talk about too much today, but there are a few slides at the end, that deals with model parallel training. And that's the case where you're able to kind of split your model up across multiple GPUs to build even larger models than what would typically be allowed by your GPU VRAM. So that's kind of a more specific case that I'll touch on a bit at the end, but mostly we will focus on what's called data parallel training. And that's kind of the most common and most easily implemented approach. But before we kind of dive into the details of that, it's useful to, and before we kind of look at starting the multi-GPU case specifically, it's useful to take a step back and look at these, what are called collective communication operations. And so just to kind of give some background and setup into the multi-GPU setting, typically we assign what are called ranks to each individual GPU in our multi-GPU setup. So in this example, we have, for example, 4 GPUs, rank 0, 1, 2, and 3. They're typically numbered starting from 0, increasing up through the total number of GPUs you have minus 1. So the total number of GPUs you have is frequently called the world size. And so this rank is essentially just an index into the GPUs, starting from 0 and going up to the world size minus 1. And so there are a bunch more of these collective communication operations, but I've highlighted here some of the more common ones that are frequently used in data parallel training. The most common of which is likely this all reduce operation. And so in this example, we can imagine that we have 4 GPUs as shown here. Each of these GPUs have some different data stored in a vector called X, but the contents of that vector, say, for example, are different on each GPU. What we would like to do is perform some operation on that data across all of the ranks and then send that result back to everyone. So in this example, we can calculate the sum of X across each of the individual GPUs, sum all of the results on each of the individual GPUs into some new output tensor, and then send that output tensor back out to each of the individual workers. And so this is probably the most common collective communication operation. And you can essentially replace the sum with any of the common operations. And this is used very frequently in data parallel training, and it's used to essentially take values from all of your different workers and then broadcast that result back out to everybody else. So this all reduce is a specific case of what's more generally called the reduce operation. And so in this example, it's essentially the same idea, but now we only want to send the result out to a single GPU. So in this case, we would call reduce on each of the GPUs and then send the result to GPU 2, index rank 2. And so this is just another kind of a specific case of this, or the all reduce is a specific case of this reduce where you send the output back to everybody. But you can also, in certain circumstances, it's useful to just send it to an individual GPU. Another one of the very commonly used collective communication operations is called broadcast. And so the broadcast operation is used to send a tensor from one rank to all ranks. So in this example, we have a tensor X on rank 1 that we're interested in. So these might have different tensors, but we're really only interested in this tensor on rank 1. And we can broadcast X from rank 1 and then essentially all of the rest of the workers will have that same result in that tensor. So this is useful for example, if you're doing some local operations on one of the GPUs and you want all of them to have the same result, you can broadcast that tensor to everybody else and make sure that they all have that value that you're interested in. Some more complicated operations maybe are gather and scatter type operations. So first we'll look at this all gather, and this is maybe a bit more involved than the operations we've seen previously. But what this does is basically gathers all of the results from each of the different from each of your different workers and orders and basically aggregates them into a list and sends that list back out to each of the workers. So in this case, each worker gets all of the data from each of the GPUs, ordered in a sequential list that's indexed by their rank. So this is really just a mechanism for aggregating tensors from different ranks onto each rank to make sure that they all have all of the data from each of the different workers. And again, the details of this aren't important. You don't necessarily need to memorize what all of these do, but just understanding that these are kind of operations that allow you to send data back and forth from different GPUs in a well-defined, consistent manner. And these are necessary when you consider the multi-GPU training setting. And so just, to kind of give maybe a bit of a higher level perspective on what all of this is. And then finally, the last operation that I cover here is called scatter operation. And so this basically scatters a list of tensors from one rank to the whole group. So this, if for example, on rank 2, you have some tensor, or some list of tensors that is with length equal to the number of GPUs that you have, you can basically scatter this list across all of your workers so that each worker receives one index from that original list. And so this is useful for essentially splitting up some data across multiple workers so that they all receive some individual component of it. But all of this is really maybe, I don't know, the details of all of these individual operations. Again, as I kind of said, aren't maybe explicitly required to understand what's going on in the training, but it's useful to know that there are these groups of collective operations that deal with moving data back and forth between GPUs. And there are a bunch of different kind of convenience functions that help you to do that. And these are really some of the more commonly used ones, which is why I decided to focus on them. Some things to keep in mind about all of this is that so these by definition being called collective operations have to be called from each rank in order to form a complete collective operation. So it can happen that maybe one of your GPUs had some failure or had some crash during your training, and in that case, it's unable to call this collective operation. And so then what happens is that all of the rest of the workers end up just waiting for this other one that'll never be able to finish. So it's important to make sure that you know that all of these will be called from each of the individual ranks. And if for some reason one of the ranks fails to respond, the rest of the procedure or the rest of the operations can't proceed until everybody kind of chimes in. So it's kind of maybe also worth thinking about why we want to do all of this and really thinking about why all of this is advantageous. And so maybe the most obvious reason is that by splitting the data across workers and feeding data in parallel to all of the workers at the same time, you're effectively just scaling your batch size by the total number of GPUs. So if you have, for example, one batch per GPU, and you multiply and you run that same procedure across now n GPUs, your global batch size, which is just the batch size across all of your GPUs, would then be scaled by a factor of n, right? Because you now on each GPU, you have an individual micro batch of 1. And so when you do the global communication across all of the workers, you're essentially working with n copies of that batch or n copies of the model that will each receive a unique batch of data. So that's kind of the most obvious and easiest to see advantage of using distributed training. There are also some more advantages. So in particular, by having a larger global batch size, this gives you a smoother loss landscape in that you're just calculating the loss over more data at an individual step. And so this kind of gives a smoother loss landscape. As a consequence of that, you have smooth or improved gradient estimators, which are less noisy. Just again, because you're averaging over a larger global batch of data. And so your gradients are just smoother because you're seeing more data at a time. It also has the consequence that less training iterations are typically needed for the same number of epochs. So this is a consequence of just moving through the data more quickly, since your global batch of data will be split into unique copies that are sent to each GPU. You're just generally moving through your data more quickly. In order to compensate for this, what's typically done is that the learning rate is scaled according to the number of GPUs, so that your updates kind of correspond to the single GPU case. And so this has really been looked at in very great detail and many different works. There's a good example here on this large batch training of convolutional networks that really kind of looks at how all of this, these changes to the global batch size influence things like the loss landscape, gradient estimators, and things like that. So if you're interested, I would definitely recommend looking at this paper and reading in more detail. But we can see it maybe most clearly by just looking at a specific example. So this is a table that shows the number of, or the time required to train ImageNet to get it to some certain classification accuracy, and comparing the result of, the benchmark result from 2016 versus the best. I think this is probably the best time in 2019. They're able to go from back in 2016, taking roughly 29 hours across by using 8 Tesla P100s. And they're able, by scaling that up, essentially just using pure data parallel training to scale their training process up across more processors, they're able to decrease the training time, obviously, very significantly, down from 29 hours to just 1.2 minutes. And this is really entirely just a consequence of using more GPUs, which results in a larger global batch size. Everything else being the same. I mean, I don't know the explicit details between these two Tesla GPUs, but the real speed up is coming from this data parallel training. So how does this actually kind of look like in practice? So if you compare to the diagram I showed previously, where you have just a single GPU and the data being fed sequentially, we now have multiple GPUs. So this is just, again, an exact copy of the diagram before, but now we have one network on each GPU. So we copy and we maintain identical copies of the neural network on each of our GPUs. And at each iteration, we feed in some unique subset of the data to each of the GPUs. So for example, GPU 0 would get some mini batch of data, GPU 1 would get some different mini batch of data, and so on for all the rest of your GPUs. You calculate the forward pass through the model from each of the GPUs, calculate the loss, and then what you want to do is really do an all reduce on the gradient values. Use that to update the weights, and then and then broadcast the weights back to each individual GPU. And by doing this, you ensure that each GPU always maintains identical copies of your model, and that they are only ever computing the loss with respect to the local batch of data that they receive. So there are a lot of very well-written blogs and posts and documentation on how to do data parallel training with different frameworks and backends. So probably the most popular at this point would be PyTorch distributed data parallel. So there are some very good links here and here on, I think both from PyTorch documentation on getting set up with distributed data parallel, all of the different changes that are required to your code, how to deal with data, and so on. And so these are really some good references on how to, if you want to learn more about the details and what really needs to be done behind the scenes. There's also this really good link from Hugging Face on efficient training on multiple GPUs that really goes through step by step what the different parallelism techniques kind of unlock and allow, what they essentially allow for. And it's just a really good, really well-written blog post. In addition, there's also another library called DeepSpeed, which is written by Microsoft and also has an implementation of distributed data parallel training that also provides some additional features that I won't really get into details here, but it's essentially a library that provides distributed data parallel with some other really nice features that's written by Microsoft. And they also have some pretty good documentation on how their library handles distributed data parallel. This is just another diagram. It's not really useful, but just to kind of, again, show what's really going on here. In this case, each of our GPUs, as you can see, receives and maintains identical copies of the model. At each training step, they get some unique subset of the data, calculate their forward pass as they would normally, and then following the forward pass, there's some mechanism for aggregating all of the gradients and then redistributing the weights back out to everyone. So yeah, as I've kind of already mentioned, the data parallel training approach is typically much easier to implement, and there are a lot of different libraries that support it and allow you to use, take advantage of using multiple GPUs. Not to, I don't know, so shameless shout out, but I have another library that I personally maintain for dealing with distributed data parallel training and things. This that I use and I kind of like, but again, a lot of them contain very similar implementations and are all used to do the same thing. So the specific framework you pick is less important. And yeah, so it's typically easier to implement, and there are a lot of different libraries that provide it for you. Just to kind of recap how it works, each worker has a complete identical copy of the model. The global batch is split into individual mini batches that are split across workers. At any given forward step, each worker only computes the corresponding loss and gradients from their local copy or their local batch of the data. And then before updating the parameters in the model, the loss and gradients are averaged across workers, and then the updated weights are then rebroadcast out. So this is kind of a more detailed view of how this looks. So each of the GPUs during the forward pass calculates the loss, uses that to calculate the gradients. And then there needs to be this kind of barrier operation to make sure that all of the different workers are now synced up and have reached this same point in the forward pass. And so this is actually maybe a kind of important step that I hadn't mentioned about before, is that in order for the average gradients to be calculated, you need to make sure that all of your workers are at the same step. And so it can often happen that maybe one GPU gets a bit ahead, and so it will then need to wait until all of the rest of the GPUs have reached this common point, at which point it can then calculate the average gradients and then backpropagate the weight updates. So there are a few details I've kind of glossed over here and how this is actually done or implemented in practice, and some things you kind of need to be explicit about and keep in mind when doing this. The most important of which is that you need to make sure that at each individual training step, you need to make sure each worker is receiving unique data, since otherwise, you're not really taking advantage of having multiple GPUs. And so this can be actually somewhat non-trivial, so that you need to figure out a way to do that depending on your specific data setup. Typically, it's usually done in one of two pretty common ways. So the first being to manually partition the data ahead of time and assign basically different sections of your data to different workers. And that's maybe the more commonly used approach, but has the disadvantage of that needing to be done and kind of coordinated ahead of time. But as long as you're able to coordinate that ahead of time and make sure that you can send different chunks basically to different workers, then that's a pretty straightforward method of doing it. Alternatively, you can essentially just randomly select a mini batch from some global data set that everybody can see. And if you were to, kind of do this random selection approach, you need to be very careful that all of your workers are receiving different random seeds. And so that each time they go to grab a different random subset, they're grabbing, different subsets respectively. That's maybe a bit more complicated, but has the advantage of being able to be done, kind of dynamically at runtime. But again, it's really just being explicit about making sure that each of your workers are always getting different data. And obviously there are ways to check that. Obviously you can just look and see, but again, it's something that you really want to make sure that you're explicit about, and can otherwise kind of cause these very subtle errors that you might not see, right? So if you aren't explicitly checking that they're all getting different data, the training might still progress as you would expect, but you're not actually taking advantage of them having multiple GPUs. It would be this, the exact same case as having a single GPU. So that's one thing, is dealing with the data. Another kind of subtle or important, kind of important but subtle point in all of this is that when you start the training, so either at the very beginning when the weights are all randomly initialized, or when you're restarting from a saved checkpoint, you need to be sure that all of your workers are initialized consistently. So probably the easiest way that is done is to load. So in the case where you're loading from a model checkpoint, is to load the model only on one specific worker and then broadcast the model in optimizer state back out to the rest of your GPUs. And by doing it this way, you ensure that you're only performing the file IO from an individual worker and then sending that exact copy out to everyone. This is kind of useful because in the case where you tried, if for example, you were to try to read from a checkpoint on all of the different ranks at the same time, this can lead to what's called a race condition, where you basically have multiple different workers trying to read from the same file. And that can lead to just, unpredictable behavior and, cause your program to hang or any other variety of different hard to track down bugs. So it's usually generally good advice to try to only do file IO from one specific worker. Typically that's done from the rank 0 worker. But by doing file IO and all of this only from a single worker and then sending results to different workers using collective communication as needed is typically a much safer approach, or the generally preferred approach. So in all of this, there are a lot of kind of subtle layers and things that can have performance impacts on the kind of global performance. So one of the most common causes of poor performance can be poor IO utilization. So it's important to try to use parallel IO whenever possible. This could really, doing parallel IO effectively and making sure that you're doing IO in a scalable manner from each of your ranks could probably be its own week-long talk in and of itself. So I don't have time to get into all of that today, but there are a bunch of different techniques and kind of changes you can try that might help. So most practical and big scale training, you would want to read data from each of your different ranks and use MPI to scatter that data to different ranks. And there are a bunch of different kind of techniques or tricks you can try to use for very large scale training runs that'll really optimize your IO performance. Another thing to maybe keep in mind during all of this is that when you're just kind of thinking about performance generally, it's useful to remember that the computation obviously stalls during communication. And so whenever you are performing some collective operations or you're waiting for data to be sent back and forth to different workers, you are basically waiting. You have to wait until that operation finishes for the computation to continue. And so making sure that the communication is overlapped well with the computation is another kind of important thing, but again, maybe beyond the scope of this talk. But really just keeping in mind that whenever you have to have workers talk to each other, that basically nothing else can proceed until they've kind of finished their chat. There are a bunch of other specifics about data storage, mostly specific to Lustre, which is the file system used on the ALCF systems. There are tricks related to preloading data and loading data to CPU and transferring it back and forth to GPU. And again, this could really be its own talk, but I don't really have time to get into it. But there's a lot of I/O related component. There are a lot of kind of knobs that are related to I/O performance that you can tune and that might give you better performance. And that's usually the most common area where poor performance comes from, is not using I/O correctly, in my experience at least. And yeah, so I guess that really is at a very high level overview of distributed data parallel training. And this is, again, as I've mentioned now, by far the most common, and is what's most typically, if you usually hear somebody say parallel training, they're typically referring to this data parallel setup. Again, just because it's very easy to implement, it requires very minor code changes. And it kind of comes built in with PyTorch these days. So that is kind of a high level summary of data parallel, and that's all I want to say about that. And so then the next kind of parallelism technique or strategy is what's called model parallel training. And so this is a completely different training setup than what we saw previously for data parallel. And so in this case, what you do is actually split the model weights up over different GPUs. So in this kind of cartoon example here, you can imagine GPU 1 has some subset of the weights, GPU 2 again has some distinct subset of the weights, and so on, where basically each GPU only has some local subset of the weights. This is obviously just, you can kind of imagine a much more complicated parallel training technique, because in order to even compute the full forward pass, there's this communication that needs to be done between GPUs, and so to make sure that they have all of the weights that they need to calculate the forward pass. And so this is just, you can kind of imagine a much more complicated situation. And so there needs to be this obvious communication whenever there's data flow between the two subsets. There are a few libraries now that are looking at implementing this. Maybe the most common or the most popular was this library from NVIDIA called Megatron. This has kind of now been forked and modified, and we have a local version that we have been using for some large language model training. And it's linked here if people are more interested. There's also more recently this Nanotron library from Hugging Face that is relatively new, but is sort of Hugging Face's answer for model parallelism. So I know that they're still missing a variety of features, but it's kind of a work in progress. And so those I kind of would say are the two main libraries that are looking at model parallelism, as far as I'm aware. But it's very difficult to implement at a library level, because the details of how the model end up getting split up are very highly dependent on the specifics of your GPU setup, the specifics of your model setup. And so it's kind of very hard to generically write a model parallelism approach that will work, for an arbitrary model and for an arbitrary setup of GPUs. But there are some libraries that are looking at doing it, and that mostly focus on some of the more common architectures, which is what these two do. We can look at a very simple, just to kind of maybe give some insight into how this would actually proceed in practice. We can look at a very simple example of model parallel training. So say, for example, we have 3 GPUs, 0, 1, and 2. Each GPU only has their individual weight. So GPU has weight 0, GPU 1 has weight 1, and GPU 2 has weight, W2. So and we want to calculate the full output, which is Y is equal to the sum of each of the weights times the input on that GPU. So in order to calculate this whole global sum, we first would need to compute. So the data first gets passed into GPU 0. Using that, we can compute W0 times X0 and, aggregate that output. Take that output, and now the next thing we want to compute, say, is W1 times X1. In order to compute that, we need to send this result over to GPU1 so that it can persist, so that it can have that data and proceed with that computation. Once you have this result Y1 on GPU1, you can then take that result and send it to GPU2. Once GPU2 receives that result, it can then proceed, or it can then calculate the final result. This should be a plus sign here, actually. And yeah, and then it will be able to compute the final result. So in order to compute the actual output, you need to basically compute it step by step on each GPU. In order for each GPU to carry out the calculation, it needs to get the corresponding data from all of the rest of the GPUs. So this is just a very simple example, and you can see, just looking at this, that this is a non-trivial algorithm that you would need to implement for sending the weights, making sure that they have everything they need to carry out the calculation. Once they can carry out the calculation, then you need to figure out where to send the data to next. And so really, this is all just to say that it's really quite involved, and is definitely, pretty non-trivial for any realistic applications. So I think that was about all I wanted to lecture and blab at you guys about from the slides. The second portion of today's material is this hands-on section. So the details of this are in this README here, and I will attempt to try to do it live now for everyone, but people can obviously feel free to follow along and do this on their own. But what we're going to do is use distributed data parallel training, which is the approach we just saw, to train a large language model on multiple nodes of Polaris at ALCF. So I think all of the previous sections in this series have used Jupyter Hub for all of the, kind of interactive sessions. So this might be a bit different. So for anybody who runs into errors or does not understand any part of this, please reach out in the Slack and we can hopefully try to get you sorted. But I will also try to run through it now so everybody can see. So basically what you would want to do, starting from your local machine, is log into Polaris. Hopefully people have done this already, so this isn't the first time. Then you're going to want to submit an interactive job on, we'll just use 2 nodes, and we'll ask for an hour. Sometimes these can be kind of slow to set up, so the trick I like to use, a trick I like to use is launch one in one queue and another in the other queue. See which one starts first. Usually you have pretty good luck and one of these will start up relatively quickly, but awesome. So pull this one. So here we are in the hands-on section. So the first thing we want to do is launch this job. We did that. Next step is module. Next step is module load conda 1004 conda activate base. Then, okay, that's done. Now you need to clone the repo. So we'll be using this library I've kind of been working on called Wordplay. It's essentially just a fork of Andre Karpathy's NanoGPT with some kind of additional features I've built in. So if anybody is interested or wants to learn more, I think there's a link here. You can read more about it. So that's that. Clone the repo, navigate into it. Now we want to make a virtual environment on top of our existing Conda environment. So make a directory to hold it, DNB. Can everybody read this okay? The font size and everything is okay?
Yeah, it looks good.
Perfect. So make this virtual environment, make this directory for holding the virtual environment. create the virtual environment, Python v, where it lives. And then you need to make sure to pass this system site packages flag, because that tells the virtual environment to use the site packages from the parent conda module. So it pulls in all of the optimized PyTorch and MPI builds of everything. Once you've built the virtual environment, you can then activate it. That'll put you in that virtual environment. Once you've done that, the next step is to install the dependencies. So we'll first install this wordplay, Python 3M. So this, for, I don't know, sometimes command line flags are not obvious. So this Python 3M, I like to do Python 3M and dash, Python 3 pip install, as opposed to just pip install, because then this is always explicit about which Python you're using. Install -E means perform an editable install. So that basically means install as, install using this file, using this local file. And then, pip install. The dot basically just means install this directory as an editable install. So we'll run this. So take a second. All right, so that installs. Now you need to install this library, easy peasy. Again, just another library I've been working on that I find useful, but there's a URL here if people want to read more. So again, this just consists of cloning that repo. That should clone it, and then you can install it. This dev add-on just gives me some additional packages. I need to fix some things, that's why I think. But this should install that easy peasy library. And this, the reason I kind of like it, or the reason I wrote it and use it, we'll see here in this next step, is that it provides some pretty useful shell scripts. So let this finish installing. So in particular, it provides these methods for saving the job environment. So for example, you launch a job on Polaris. When you get launched into that interactive job, it populates your environment with all of these PBS environment variables. You can call this source save job env. And what that'll do is write out all of the PBS variables in your current environment to some file in your home directory. And basically do some logic to figure out how many hosts you have, how many GPUs live on each node, and then using that information to calculate the total number of GPUs available in your job. And then it just does prints some additional information, which hosts, and then defines this kind of convenient alias launch that bundles up all of the flags and everything you need to pass to MPI exec to use all of the GPUs available in your job. Currently, there's a big little bug in it that I have to work out. But there's additionally this get job env. It actually defines things. And so again, this just basically reads in from this file. The details of this aren't necessary to understand, but they're just basically these convenience functions that define this alias launch. So launch gets alias to the MPI exec command that you need to launch your distributed training. So once you've done that, gone through the easy peasy install and ran this set and get job environment, the next thing we need to do is prepare the data set. So for this example, we provide this Shakespeare this Shakespeare character data set, which is just the contents of Shakespeare's works, tokenized at a character level. And you can set up that data by just running Python data. Yeah, data Shakespeare. So running this will basically work through the tokenization and uses Hugging Face data sets. So this was then prepares that data. That's all you need to do for that. Then once you've prepared the data, you're really ready to launch the training. So if you navigate into this source wordplay, you can then launch the training. So this launch is basically just this MPI exec command, which tells this, it basically defines how to launch some executable across all of the GPUs. What we want to launch is Python, and we're going to launch Python on this main.py file. We want to run the Shakespeare experiment. So this basically just defines a pretty relatively small model architecture and some common, some additional options for the run. We want to use the Shakespeare data set. We want to use DDP for the distributed communication backend. Train for 100 iterations. Print out information every 5 steps, and we're going to skip the compile for now. This should print out some information connected to yada yada, found the executable, launching application. And now if everything works as expected, it'll then run the data parallel training. Print out some information. Then prints out some information so you can see it does some handshaking between all the GPUs and identifies rank 0, 1, 2, 3, all the way through 7. So right now we're running, maybe I skipped over this initially, but we requested in our Q sub 2 nodes. So each of the nodes on Polaris, as we've seen before, has 4 GPUs. And so that's where this is coming from. We have 8 ranks total, 4 on each node. And so this prints out some information that, just to check, it's able to talk to all of them, set them all up, initialize them all correctly. You can see we're using device CUDA on global rank 6 or 7. There's also this idea of the local rank. So this would be the rank from 0 to 3 on the individual host, and then which host we're on. So it'd be 0 or 1. And so then it goes on and prints all this additional information, what the PBS node file is, the different hosts, so on and so on, what data type we're using. So by default on CUDA, it will use, I guess, bfloat 16. Again, just some more logic, making sure all of the devices are initialized correctly. Then, so actually another thing, so it by default will use this weights and biases library. So if you have never used this before, I think you'll need to run like weights, and I think it's like 1db login. And it'll force you to create an account, unfortunately. I think it's pretty convenient and worth making an account and using. I use it very frequently and very heavily in my personal research. And so I would recommend, getting familiar with it, trying it out, using it. It's useful for tracking metric values for across different experiments. So for example, in this run, it tracks things like the loss, timing information, so the forward, backward pass, so on and so on. And you can really use it to, track metrics across experiments, however you would want. But I think it's a useful tool and worth, familiarizing with a little bit. So it prints out some information about weights and biases, prints the link to the run URL. as well as what project it's a part of. Then prints out some additional config information. So these are the values that were passed when the program started up. So for example, we didn't specify the device or seed or anything, just let that all be taken care of automatically. Specifics about the model architecture. So I think it's prints out from here somewhere. Details about, yes, so we're using 6 layers, each layer with 6 heads, an embedding dimension of 384, sequence length of 256, dropout, batch vocab, and batch size. You've seen all of this previously in the LLM talks. This specific model configuration gives a model architecture of 10.6 million parameters. So this is obviously relatively small, but this is just kind of a simple example. So it prints out all of this information, some information about the startup time, and then essentially proceeds with the training. So at the very beginning, it prints out this legend, which contains all of the abbreviations that are used when it prints out information. So it prints out things like the step, current loss value, total time elapsed in the forward and backward pass, the amount of time spent in forward, amount of time in backward, and then some additional convenience metrics like the number of samples and tokens per second, and then the most recent value of the train loss and the validation loss. So you can see then once the training starts, every 5 steps, it prints out all of this information. And you can see kind of as you would expect, the loss decreases over training, which is good, obviously, a good sanity check. At the end, it then saves some checkpoint, saves the model checkpoint out, and then finishes the run. And so that really is a very simple example, but essentially covers everything I talked about and encapsulates all of the ideas you need to know for distributed data parallel training. If people want to play around, you can change things. So if you run like help, it'll tell you about all of the different configuration options you can override and change if you want. So things specific like the model architecture. There are mechanisms for, I'm not going to cover it in detail, but you can instantiate from the GPT-2 variant architectures. So you can either start from scratch or resume from the checkpoints on Hugging Face. And there's really a whole bunch of different functionality in here you can play around with and try on your own if you're really interested. So you can change anything about the model architecture, number of layers, heads, so on, what optimizers you're using. It's also compatible with any Hugging Face data set. So you can, at the beginning when we were preparing the data, we ran this Python data Shakespeare character example, but this will also work with any Hugging Face data set. So for example, to use like the Yelp review data set, you can run data there, and then the name of the Hugging Face data set. So if you run Yelp review full, for example, it'll download, tokenize that Hugging Face data set. And then you can specify, you can pass that to the trainer and it'll use this instead of Shakespeare, which is probably a bit more interesting. But you can really play around with it. And I encourage people who are interested to try changing some of these different settings and, poke around a bit if you're really interested in. I think it's a pretty useful and convenient library. Obviously, I'm biased, but if people are interested or see something that catches their eye or just anything that seems interesting, please reach out. I'd be more than happy to talk about it. You show us about prepare for the image. I'm not sure I exactly understand. So for image data, that is a whole nother can of worms. And dealing with multimodal data sets. If that's what, I'm not sure if that's what you're asking, but so this is strictly text-based at the moment. Dealing with multimodal image-based data is definitely beyond the scope of this talk and is kind of an open air, open question in some respects. So I don't know, again, I don't know if I answered that question or if I even understood it correctly. No problem. Yeah, sure. Cool. Yeah, so now here, this is again running now with the Yelp review data set. And yeah, so there's stuff I didn't cover. There's additional logic for prompting the model, obviously. So there's a mechanism built in to generate text from your pre-trained model. There's also this kind of, I don't know, maybe neat example that I've gone through, not in this talk, but in previous talks I've covered before. Where you can really use the Shakespeare data set to train a model that talks like Shakespeare. So this is an old example I've gone through, not here or not during this session, but it's kind of an interesting self-contained example if people are interested and would like to learn or see it more. That basically runs on a single GPU, but uses that Shakespeare data set to train a model that'll essentially talk like Shakespeare. So you can see before the training, the model is just, if for a model that's randomly initialized, you get basically random outputs out. So I prompt the untrained model and ask, what is a large language model? And it just spits out gibberish, kind of as you would expect. And then after some very brief training, you can, maybe not perfect, but you can see it'll kind of start to talk like Shakespeare, at least look a little bit more like it. Then you can train for a bit longer. And then finally, by the end, you can have a little model that, doesn't really make a whole lot of sense, but talks like Shakespeare would, which is kind of cool, kind of a little interesting. But yeah, so there are mechanisms for prompting the model and generating outputs. Obviously not covered here in the training aspect, but yeah, all of that exists if people, want to play around more. And with that, wow, look at that, right at 4 o'clock. I suppose that is about all I wanted to say. If there are more questions or anybody wants to talk any more about this, like I said, please feel free to reach out. Be more than happy to talk about it more or answer questions anybody might have or issues with running things or anything like that.
So before we have our science speaker for today come in, we have about 10 more minutes. So I think it would be a good opportunity to answer any questions if anybody has specific things, or if there's any troubleshooting that people want to do, since obviously hands-on is good and can also sometimes be kind of fast. And we could also give folks, I don't know, 5-7 minutes to sort of play around with themselves and then maybe come back, do a quick debrief before jumping in to the science talk. So I don't know, we have 10 minutes to sort of use as we will.
Yeah, just catching up on the Slack messages. I don't immediately see any troubleshooting issues, which is always a bit of a relief. And looks like there are some questions, but looks like people have been answering them. So thank you everyone who's been.
I see one good question from Zoom is just there any homework for the session? And if there is, like, where does it live?
Excellent question. Way to keep me on my toes. At the very bottom of these instructions, yes, this very final list item is to just, and really there is, since this is a more or less pre-canned example, there is not really much you guys can do to adjust things. You can obviously change the parameters and change how things are run. But really for homework, I just want to make sure that people are able to run it and have kind of worked through the instructions. And so really any proof that you're able to run successfully, either a link to a weights and biases run, or capture the output in a log file and send that over, but really just sort of any sort of record that you were able to run the training successfully, yeah, will count. Good call, because I did not mention that. Side question. I love when people ask me about my terminal, my colors, my setup. So excellent question. So I use a terminal called Kitty. It is, yeah, I think it's cross-platform. So I think they have it Windows, Mac OS, and Linux. It's a bit more maybe involved. The configuration and everything it's not very GUI friendly, but has a lot of pretty neat features. So for example, like some people probably noticed that when I initially logged into Polaris, instead of using SSH like you normally would, there's this kind of convenience function that will share the login credentials across different sessions. So you only ever have to type in that, mobile password once, which is something really convenient, something I like. Yeah, and it just has a whole bunch of customization options and things like that. So for people who are into that, obviously it gives you, an infinite rabbit hole to dig down, which is why I use it. And then, so that's the terminal plugin so I use Z shell with a modification of what's I guess it's power line. Okay. So it's a theme for Z shell. And I just basically use a modified version of it. Be happy to share the config too if people want. So like an alias and bash profile. So then maybe I missed is what, like an alias in the bash profile. Yes, so it's not exactly an alias. I think if you're talking about the Kitty SSH function, I don't exactly know how that works behind the scenes. I know that it's some feature of the terminal emulator. So I don't know exactly how it's done behind the scenes, but yeah, I don't know. It's a bit beyond my knowledge, at least. Although it is actually, I guess it is just an alias to this kitten SSH function. So again, I don't really know.
We have one question in Slack.
I just saw that, which is a
Yeah.
good question. So after successful training, how can I test the train model? So, oh, did my job end? Wait, no. So again, it goes back to why I like this easy peasy library. If for some reason you get disconnected in the middle, as long as you run this save job env at the beginning, you can always log back into a node that's part of your running job and reactivate that environment. And so with that is just to say, getting back to the prompting question, let's see if I can get the exact syntax for it. Let's see now. I added some so basically what I just did is added some logic to, at the end of training, run this evaluation code here. So basically I define some query, and then you can generate text by calling the evaluate method on this trainer object with some query string. And so let's see. that might not work exactly at the moment. It should. I will actually look at fixing that immediately after this because that's one of the, issues of doing things live. So something like that. I can, that's the basic idea. I don't know why it's not working exactly at the moment, but once you have a trained model, you can basically call a query by running this evaluate method on it. So this is a bit rough around the edges. I apologize.
Okay, well, thank you very much. This is going to be a slightly different topic in a sense, because it's going to be an overview on the science we are doing on using artificial neural network, and namely neural network quantum states. But let's take a step back first. So everybody is familiar with what an atom is, and this is probably a wrong picture of the atom, because we have somehow classical electrons orbiting around the central nucleus. But what we are really interested in this talk is this tiny, very dense object that sits at the very center of the atom, which is the atomic nucleus. And nuclei are basically made of protons and neutrons, and they are self-bound. So protons and neutrons bind together because of the strong force, and they form nuclei from the lightest one, which is the deuteron, just one proton and a neutron, to the heavy radioactive nuclei, say uranium, and even heavier than that. And here at Argonne, we have an experiment at Atlas, which is not the Atlas sitting at the LHC, but it's the Atlas Tandem Accelerator System that actually studies properties of nuclei. And there are many nuclei. This is the nuclear chart. Is the nuclear physics equivalent of the charts of elements. On the x-axis, we have the number of neutrons. On the y-axis, the number of protons. And in the center in black is the valley of stability. So stable nuclei, because of nuclear forces, tend to have the same number of protons and neutrons. But there are some open questions. For example, where is the neutron drip line? So if we keep adding neutrons to nuclei, when do the nuclei stop being stable? So they start losing neutrons as we add them. And these questions are important even for astrophysics. So if we want to understand the origin of elements heavier than iron 56, we know that they are not produced in the stellar evolution cycle, and we need to look at for example, events that are like neutron-star mergers. So nuclear physics is looking into many of these questions. And in addition, nuclei are also used as detectors. So understanding nuclear dynamics is important for advancing our understanding of the standard model of particle physics. Here at Fermilab, the nearby laboratory, a beam of neutrinos is produced, and then it travels for hundreds of miles underground, and it's detected in South Dakota. And while traveling underneath the ground, neutrinos oscillate, so they change flavor. And basically, the spectrum goes from the one on the left to the one on the right, and some electron neutrino may appear. The way these neutrinos are detected is by scattering them of nuclei and reconstructing the properties. So the energy dependent of the neutrino flux is reconstructed by the observed scattered protons and neutrons. And the dynamics of the scattering really depends on the interactions between protons and neutrons. So scattering on a nucleus is very different than scattering of individual free protons and neutrons. And also, if one wants to see whether neutrino is its own antiparticle, typically this is done in nuclei. And nuclear corrections, so again, nuclear dynamics plays a critical role in this discovery, in this experiment. And finally, nuclear dynamics play also an important role in neutron stars. And probably the discovery of the century is the observation of gravitational waves from spiraling compact objects in the sky. And what happens if two neutron stars, so two very compact objects, basically 10 kilometers in radii with the mass of the sun, and even more than that, they start orbiting and spiraling around each other, Well, some material from one star falls into the other, and the rate of infalling material determines the gravitational wave signal. But again, how much material really falls from one star to the other depends on how strong nuclear interactions are. So again, our calculations are relevant for studying these properties too. So as you can see, nuclear physics enter a different domain of physics, not just nuclear physics itself, but it also impacts high energy physics and astrophysics. Now, the underlying theory of strong interaction is known, is quantum chromodynamics, but it's non-perturbative at the scale of nuclear physics. So what we typically do, we construct effective field theories. So we have rigorous way of constructing interactions that involve nucleons, say neutrons, protons, and pions, and we don't worry about the underlying dynamics of quarks and gluons. And basically all we are left with is a non-relativistic Hamiltonian, very similar to the one that you see in quantum mechanics 1 courses, or very similar to the one that is used in quantum chemistry to solve the structure of atoms and molecules. And this is really the Hamiltonian. It's a quantum mechanical operator containing kinetic energy, two-body interaction, basically two nucleons interacting with each other. But since nucleons are not elementary particles, we also need to include a three-body force, because basically the structure nuclei gets the nucleons, so protons and neutrons get deformed once they're close to each other. Now, if we have this Hamiltonian, we want to solve the quantum many-body problem, which is an NPR problem. It's actually the complexity is factorial, grows factorially with the number of nucleons, with the number of particles. And this is actually the problem statement. So nuclear forces are spin and isospin dependent. So the potential between two protons, say, depends on whether one proton is spin up and the other one is spin up or down. So the wave function cannot be factorized with a wave function describing spin up particles and spin down. And so our coordinates are really the spatial degrees of freedom, x, y, z, the position for each of the nuclei, then the spin of each nucleon, whether the nucleon is up or down, and the isospin, whether the nucleon is a proton or a neutron. And nucleons are fermions, like electrons if you want. So this solution that we want to find is anti-symmetric. If you exchange two particles, we need to get a minus sign. Now, conventional quantum Monte Carlo methods scale exponentially actually with the number of particles, because of the spin isospin dependence of the nuclear force, we need to keep track of all possible spin isospin combination. So if we have, say, 3 particles, there are 8 possible spin isospin states. 3 spin up, for example, or 1 down, 2 up, and so on and so forth. And so using conventional quantum Monte Carlo methods, even using supercomputers like Aurora, Polaris, we are limited to light systems, say nuclei with up to 14 particles at most. We can do very precise physics there, but we are limited to these light systems. To go beyond it, we are developing neural network quantum states. And the idea really here is to represent the quantum mechanical anti-symmetric wave function in terms of an artificial neural network. How does it work? How does this work in a nutshell? Well, we want this wave function to be anti-symmetric. So the first ansatz that we tried was the so-called Slater-Jastrow ansatz. So it's the product of a symmetric factor e to the jx times an anti-symmetric factor. So that if you do this product, then the resulting product is completely anti-symmetric, right? Because you have something symmetric times something which is anti-symmetric. Now the Slater determinant is the anti-symmetric part, and each orbital, which is represented by a feed-forward neural network. But then the Jastrow has to be permutation invariant. And of course, one way to make it permutational invariant is to symmetrize by hand. So we apply a neural network, say little j, to x1, x2, and x3, and then by hand, we consider possible permutations. Well, if one follows this approach, clearly this scales factorially with the number of particles, because as you grow, as you keep adding particles, then the number of permutations that you need to consider grows very fast. So it's not feasible. So what we did to actually construct a permutation invariant function is to use the deep set architecture. And the idea here is to apply the same function phi to all particles, and then sum over them so that the ordering of particles is destroyed, and then apply another function rho to this sum. And both phi and rho are artificial neural networks, and one can prove that this representation is universal. And not only universal, but all permutation invariant functions can be sum decomposed. So this is basically, there are two papers discussing this into great detail, and we make use of it. Finally, to optimize the wave function, what we do, we can't just, the idea is to minimize the expectation value of the energy, but we don't really, we do somehow a fancier version of this algorithm. What we do an imaginary time projection, a projection in imaginary time. So basically, we apply the imaginary time projection operator 1 minus h delta tau to the starting wave function, and then we change the parameters so that they match the imaginary time evolved function. Basically, it's a improved version of the stochastic gradient descent. As you can see, the new parameters P of t plus delta t are Pt minus the learning rate delta tau times the gradient gt, but there is a preconditioner s to the minus 1, which is the quantum Fisher information matrix. Basically, in the language of artificial neural net, in supervised learning language, this is basically nothing but natural gradient. So we account for the curvature of the space. Now, some of the results here in this first work, we tested our approach on a two-body system, and we actually proved that the energy per particle matches the exact one, because in this case, the system is small, so other methods can be used. And after 200 training steps already, the energy really matches the one obtained with conventional techniques. But this was not enough. For the two-body system, that worked, but then we realized that this ansatz was a little bit too restrictive, and we had to generalize it. And to do that, we actually expanded the Slater determinant to add some fictitious degrees of freedom, hidden degrees of freedom. So basically here, we want, again, an ansatz which is completely antisymmetric. So we added to the original Slater determinant fictitious particle y and fictitious state chi. And one can prove that this ansatz is universal, so it can approximate any antisymmetric wave function. And again, we know that the wave functions of nuclei, pretty much like the one of electrons, must be antisymmetric. And this is the pictorial representation. So basically, in the original system, these three nucleons are very correlated. They're very entangled, but we can add fictitious degrees of freedom, say these blue particles. And now if we add them, if you want, the interactions among these 5 nucleons are way weaker because they mediate the original one, if you want. And so they can be solved using much simpler artificial neural networks. So in a sense, we pay the price of adding fictitious degrees of freedom to add, but we need to add fictitious particles. In any case, by doing so, now I'm showing the plot on the left, for oxygen 16, a much larger system, we can reproduce quantum Monte Carlo results by adding more and more of these fictitious degrees of freedom. We don't reproduce just the energy, but also how nucleons are distributed inside of the nucleus, which is the plot on the right, which is the one-body density. Basically, this tells us what is the probability of finding a nucleon, a proton or a neutron at a given distance from the center. Now, I'm running out of time, so I just wanted to flesh out a few more results. This is the equation. We can also compute, as I said, properties of matter that is found in the interior of neutron stars. This is actually the energy of this matter. We are simulating here 14 neutrons with periodic box boundary conditions. This is a way to simulate matters found in the interior of neutron star. And the orange points are the results obtained with artificial neural networks, wave function. State-of-the-art quantum Monte Carlo results are the black, so we agree fairly well. But in order to fight, if you want, the exponential scaling with quantum Monte Carlo, we had to use 1.2 million core hours on an Intel processor. And instead, the orange curve was obtained basically using 100 hours on an NVIDIA 100. So there is an impressive speed up. Now, let me flash this, is that we don't apply these methods just for nuclear systems, but also for condensed matter systems. Like we can study phase transitions in cold Fermi gases. These are basically a collections of spin up and spin down particles, and we can study the phase transition of them. We use a different ansatz, but here the idea really is that state-of-the-art diffusion Monte Carlo results are the blue as a function of the number of particles, and the artificial neural network instead of the orange. So we obtain better energies per particle in much better agreement with the experimental constraints. And finally, back to nuclear physics, the very last slide. We are studying, again, neutron star matter using the ansatz that we used for cold atoms. And I just wanted to show you this video. So in the crust of neutron stars, there are protons and neutrons. But it's still, basically the idea is that nuclei are formed, but these neutrons have a lot of neutrons. And there are different possibilities. Suppose that we have 4 protons and a bunch of neutrons. We can have a liquid phase in which the protons just fly around. We can have instead clusters of deuterons, so just deuteron nuclei flying around. We can have clusters of helium-4, so 2 larger nuclei, but not all the protons together. We can have one big cluster of beryllium-8, which is a nucleus with 8 nucleons, and then a gas of neutrons. Now, with conventional quantum Monte Carlo methods, in fact, with any of the conventional quantum many-body methods, this is impossible to describe. One cannot describe the self-emergence of nuclear structures. And this is what happens using in the free case. So if there are no correlations, I'm printing here the positions and the nature of these particles. Orange is the protons and blue is the neutrons in neutron star. And as you can see, this is a pure liquid phase. There is no correlations at all, no interactions at all. But what happens if one turns the interaction on, optimizes the neural wave function? Well, we get the clustering. As you can see, protons can stick together the whole time. So we have the formation of a beryllium-8 cluster basically in the center of the simulation box, and this flies around. There are 3 neutrons streaming, but all the protons are together. And this is only possible, it's possible to simulate this kind of matter with this kind of accuracy using neural network quantum states. Conventional quantum Monte Carlo methods will fail. Oops, sorry, these are my conclusions. Basically, neural network quantum states can efficiently approximate quantum many-body wave functions across different energy scales. It has been shown not by us, but by other groups, for example, Google DeepMind or DPFL or Microsoft. Atoms and molecules. We did cold atoms, as I showed before, but our main focus is atomic nuclei and neutron star matter. But what we are really interested in now is to take our real-time dynamics, real-time quantum dynamics, which is a very well-known NPR problem, but an accurate description of the latter is relevant for fission, for fusion, and neutrino oscillation experiments. Thank you very much, and I'm ready to take questions.
Thank you, Alessandro. I see one question in the Zoom chat from Will. Will asks, since the conventional EFT quantum Monte Carlo method scales really badly, how can you verify that the artificial neural network results are correct for bigger systems than conventional methods that conventional methods can't handle just out of the sheer size?
Yeah, so that's a good question. There are several tests we can make. So typically we can use quantum Monte Carlo conventional quantum Monte Carlo to take on larger systems by doing by making some approximations. And the idea is that we compute the same systems using neural network quantum states. And since this is a variational method, if we get a lower energy, then we can claim that this is more accurate than quantum Monte Carlo results. Then there are other methods that are more approximate than quantum Monte Carlo and that scale polynomially with the number of particles, and we can compare with them too. But ultimately, the comparison is going to be with experiments.
Excellent. Thank you for the answer. I think looking at the time and seeing no other burning questions, I think we can wrap today. So thank you so much, Alessandro, for coming and presenting. Thank you, everyone, for participating today, and we will see you next week.